Alright, so one of the, I don't know, I think the cool things about the different math that we do, especially like exponentials and logarithms, are like the different applications that we can use them in. And that's because like exponentials and logarithms have some really like direct applications. So like some of our stuff, you know, like when we do like linear equations or even like quadratic equations in our Algebra 1 and Algebra 2 classes, like we can look at like applications or real world stuff, but it like we're kind of simplifying the actual real world application in order for it to work. Versus our exponentials and logarithms are like the actual equations that we use to represent some different things in the real world. I mean, and although like I think math is just really cool for like the sake of math, most people like use math more because it helps us to solve real world things. So do any of us know of any of the applications for exponentials and logarithms? Interest, so like sales, interest, a lot of like businessy type stuff, yeah? Any others? Is there anything else that grows rapidly? Population, yeah, so like population of people, depending on the year where you're talking about. Also like population of like bacteria, so like how bacteria spreads is a really common one because it spreads very, very rapidly. We're actually going to look at the population of fruit flies because they also reproduce at a very, very fast rate. You can also look at the population of like rabbits or like other invasive species in the areas. As well as like bacteria, you can also look at the growth or the spread of like a virus, right? That is also going to have an exponential. And then our logarithms, we don't use quite as often, but they have some cool applications. One of them is like sound waves on like how loud or like for like decibels on how loud things are. And then the other one that we're actually going to look at some examples of is the Richter scale rating when you're looking at earthquakes. So your lab is going to be, we're going to look at a couple of examples, but there's lots of applications out there. So your lab that you're going to be working on is to pick some sort of applications of exponentials or logarithms and do a little bit of research on it and kind of come up with your own like word problem type of thing on it. But we are going to cover a couple. So these are some of your growth models or your logistic or logarithmic models. By a model, it just means that's the equation that we use for that situation. The only one that you need to know is number 1. Okay. The other ones, like we won't go over 3 or 4. They're kind of beyond the scope of this class. If that's the one that you want to look into, by all means go for it. And then the other type, like this one or number 2, I would give you something that looks like that. Or if there's like other types of models, I would say like given this model, and I would give you the equation. However, if I say something is exponential growth, right, you need to know y equals a e to the bx. So that's the only one you actually have to like know. Okay. So the first one, like we said, is a business or a sales application. So this says the amount S in billions of dollars spent in the United States on mobile online advertising in the years 2010 through 2014 are shown in the table. A scatter plot of the data is shown below. So this is our table. We have years, advertising spending, and then this is our scatter plot. So just a couple of key things to look at. First, what does that graph roughly look like? An exponential growth, right? Which is why we're talking about it, right? It seems like it is growing, yes. Also, what are some other important things to look for when we're given a graph, especially like that has an application? So like we have 2 different what? Axes, yep. So it's important to make sure that we look at what those axes represent. So what does our bottom axis represent?
Year.
Year, okay. Time is an independent variable. Yes? Okay, because as of right now, there's not a way to fluctuate time. So it goes on independently. So time is what is going to go across the bottom most of the time. Versus our y-axis in this case is what? Dollars. Is there anything else about that dollars that's important? It's in billions. Which that's going to be important because looking at my data, okay, in 2010, did they spend $0.6 on spending? No, they spent $0.6 billion on spending. So that's a big difference. So one, making sure that we see what our things are labeled, and then two, if there is any type of conversion. For our year, did they do any type of conversion? Did they?
It doesn't start at 1, it starts at 10.
It does start at 10, so that's what this little means, right? Like it just means that it skipped to 10. But then two, did they put 2010, 2011, 2012, 2013, 2014 on here? No, they converted it basically from years since 2000, right? So this became 10, 11, 12, 13, and 14. Yes, no, maybe. Okay. So that's kind of the first thing is just like when you're given a set of data, make sure that we're like breaking that down, see what it looks like, see what it means, see if I have any type of pattern, which we said this looks roughly exponential growth. Which is why when we're given a growth model, it is an exponential model. So this says the growth model for the previous data is S equals 0.00036 e to the 0.7563 t. Now this model really only works between the years of 10 to 14. The farther out you go from like where you started, usually the less accurate your model is gonna be. So there's usually an ending spot for where they say you can accurately use that model. So our question then is, in what year will the amount spent on mobile online advertising be approximately $65 billion? So kind of the two key things that we want to pull out when we're looking at an application problem are, what do they give us and what are they asking for? So notice here, they give us $65 billion. So that's a given. And then what they're asking us for is the year. Yes, no, maybe. The next thing that is, we need to turn what those words mean into what our problem says. So which one of our variables represents that 65 billion? S. So this is going to be our S. And then which one of our variables represents the year? T. Okay. Because once I can break down what I'm given, what I want to find, and I know where to put them in my equation, it's very similar to what we did yesterday. We're just solving equations. But that's kind of the key to your application problems, is that we do have to break apart which things go where. So if I'm going to plug 65 billion in for S, what do I want to put there? 65, I don't need all the zeros? No, because remember our S was in billions of dollars, which is one of the reasons why we tend to like shift to some units, is because we don't want to deal with really big numbers. Equals 0.00036 e to 0.7563 t. You're going to want to have a calculator, either Desmos or just a normal handheld is fine. But most of our application problems are not going to be nice pretty numbers. They're going to be like some ugly decimals, which is okay. But that's one of the reasons why we're doing a lab instead of a concept check, because I want you to have time to like deal with those not nice numbers, not during like a constrained time limit. So, what type of equation do we have here?
Exponential growth.
It's an exponential growth. Specifically, we have an exponential equation because notice my t, or what I'm solving for, is still in my exponent, yes? So I'm trying to find the year, which means I have to solve for t. So I have to get it out of my exponent. Agree? Have we been doing practice with solving things to get them out of my exponential? Yeah. So this is going to work very similarly. So remember that our first step is that we have to divide by this stuff on the front. Remember, we have to get our E stuff by itself. Now I will say, because all of these are going to be not fun decimals, I'm going to hold off on rounding, and so should you, until the very end. Okay? We don't want to round this number and then take the natural log or something else of that, because then you're compounding your rounding error. So we only want to round our number one time at the end, if at all possible. So now I have e to the 0.7563 t power. So how do I get rid of an e? To take the natural log of both sides. So if I take the natural log of the right hand side, what are we going to be left with? Just the exponent, yep. Yes, no, maybe. Okay, so then what would our last step be to solve for 2?
Divide by 0.7.
Yeah, all that stuff, yeah. Now do be careful, because remember, once I've taken the natural log, anything that I do after that is going to have to be outside of our logarithm.
Hi, Yukon National Bank just dropped off food
Okay.
at our place, so we're bringing it to you.
Okay. You just, yep, you can just put it over here.
Okay. No, they just randomly showed up with food.
Actually, I'll take it. Alright, so then we said our last step is to divide by this thing, but make sure that you end your parentheses. Yes, which is a not nice number, but then we're just typey into whatever calculator makes your heart happy.
Thank you.
So, what do we get? Give me 3 decimals.
4003.
Okay. Yes? Alright. But our question asked us about a year. Is that a year? Not really. It's like, we also need to remember so we had to just put in 65 because S is in billions, yeah? What did we also change our years to?
2000.
Yeah, like years since 2000. So really this T represents what? 2016. Like probably in January, right? Like barely into 2016. So that would be our answer. What questions do we have? Alright, so that's one where we are given the exponential model and we're just having to like plug some stuff in and find some stuff. There are also going to be others where we're given information and we actually have to make our model. Which this is probably the toughest kind of question, is to make your own model. But we're just going to go through it step by step. So it says, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. All that means is that I am using that exponential growth formula that we had on the first page. So it just means that it's going to meet that model or equation. The experiment starts with 33 flies. After 2 days, there are 100 flies. How many flies will there be after 5 days? So, thinking of the same thing, right? If I start from my question mark, okay, they give me 5 days, and they want to know how many flies, okay? But the problem is right now, if I were to plug that in, okay, into my x, because that's what represents time, is x, I also have an a and a b. And I don't have those values right now. So I'm not going to be able to find how many flies, which is our y value. Are we with me there? Which is why they give us this other pieces of information. Because those are what's going to allow us to find a and b and eventually plug in 5. Yes, no, maybe. Alright, so the first one tells us that the experiment starts with 33 flies. So again, which variable did we say represents flies? The y value. Okay? Because remember, our independent variable, or x, is going to be our time. So in this case, it's days. Our dependent variable, which is our y, is going to represent our number of stuff. So number of dollars, like we had previously, number of flies, like we have on this one. Okay? Now, if we're at the start of the experiment, what is our time?
Oh, yeah, we start?
Yeah, like basically before we start. 0, right? Because like we are starting the experiment, no time has passed. Yes? So that means that I have b times 0. What is b times 0? 0. And then anything to the 0 power is what?
1.
1. So what are we just left with there? Just a, right? So that's nice, because now we have one of our variables that's been solved for. And that is usually going to be the case. This front number of a is going to be our initial population, or initial amount, initial stuff, whatever it is. Okay? The b value is our growth rate, and so that's now what we have to use that second piece of information to help us find. So this time, how many flies do we have?
100.
100. And how many days have passed?
2.
2. So we have 2b. Or not 2b. Right? As Shakespeare said. Alright, so again, what type of equation do I have? Yeah, it's an exponential, right? My b is in my exponent. That's what I need to find now. So it's an exponential equation. Are you okay with that? So my first step is to get our e by itself. So what do we need to do?
Yeah.
And then, how do we get rid of e? So stuff.
Non-natural.
Yeah, natural log it. So we're just going to be left with a 2b on the right side. So then my last step, how do I solve for b? Divide by 2, and dividing by 2 is also the same thing as multiplying by half. The only reason I write it like that is because it's just a little bit shorter to not have to write out like another fraction. But you could definitely put this over 2, and that's fine. But again, I'm going to leave it like this because I want to round as few times as possible to get some decimal approximation. So now, I have 1/2 natural log. That should be a 100, not a 300, times our t. So now that I have solved for a and b, what can I do? Plug in what? What was the whole reason we did all this? We want to plug in. What did we underline? 5. That's what we want to plug in. And again, you're typing all of that into your calculator. That times 5 is outside of your logarithm, so make sure that you end the parentheses as you're typing that part in.
So the t is the 5.
Correct. Because remember, my t represents time. Oh, sorry, I think I put it as x's. It should be x. But, I mean, sometimes you'll see it either way, because if it's time, sometimes we'll put it as t instead of x, but either one. X also represents time. So what do we get there? $527. Give me 3 decimals. 5. 0 8. Yes. Well, I don't think we really want parts of flies, so let's round to the nearest whole fly. So how many flies do we have? 528 flies. Which is a drastic difference from us starting at 33 flies, yes? That's also assuming that none of the flies have died off in that time, but that's how many new flies we would have. Which is still a lot of flies. Like I said, this is the longest type of question that we would have, where we have to build our own model. What questions do we have there?
How would I type this in my calculator again?
We're going to just
Okay, so it's just the second then.
And then just
I'll go at 5.
Yep. Okay, we got 2 last kinds. These ones are much shorter. Okay, so another big one. This one's actually one of our decay models. Okay, which I told you I would give you, and that's why there's this negative up in our E. It's because it is decaying this time instead of growing. And this is called a carbon dating model. So we use this when we are looking at dating fossils, bones, things like that. And the reason is because everything has carbon in it, but after something has been fossilized or dies, your amount of carbon decays. And so you can actually work your way backwards to say, okay, how much carbon do I have left will allow me to figure out how old that thing is. So R in this equation represents a ratio between 2 different types of carbons. You don't really have to know like what that is besides just it's the ratio. So like in this case, it says given the carbon dating model, which is what I gave you there, estimate the age of a newly discovered fossil in which the ratio of carbon 14 to carbon 12 is R equals 1 over 10 to the 13th. So again, we're looking for 2 things. What are our 2 things we're looking for? Yeah, so like what they ask us to find, which in this case is the age, and what they gave us, which is our ratio. Yes? And our ratio represents which variable?
Independent
R is going to be our dependent. Okay? So that's what I'm going to plug in there. And then we are solving for our t value. So again, we have what type of equation? An exponential, right? Our t is in our exponent, and that's what we're solving for. How old the thing is. Flush it. Yes, no, maybe? Okay, so our first step, remember, is that I have to get my exponent by itself. So what do we want to do first? How do I get rid of a 1 divided by 10 to the 12? Multiply by 10 to the 12, right? Or in other words, you're dividing by 1 over 10 to the 12, which is the same thing as just multiplying by 10 to the 12. Now, if I have 12 tens on top and 13 tens on bottom, how many tens do we have? Yeah, we could subtract, right? And so then the negative just means that it is on the bottom. We're okay with that. Now, technically, you don't have to do that reduction. You can still just plug into your calculator. It's just kind of nicer if I only have 1/10 instead of having to worry about the 12 and the 13 as an exponent. But it'll work anyway. So then how do I get rid of this e? Natural log it again. And I'm going to be left with still this big fraction. So then our last step is just going to be to solve for the big fraction. So how do I get rid of dividing by an 8,223? I'm already dividing, so I would multiply. Yes. But our t is also what? Negative, so I'm just going to stick a negative in front. And again, that would be our answer. We're going to get a big-ish number on this one. What do we get? $18,934.157. 5, 6? 7. And we're in euros. Yes. Which, I mean, like, for a fossil actually isn't that old. What questions do we have on that one? You ready for our last example? Is a log example. So it says on the Richter scale. So the Richter scale is the scale that is used to rate earthquakes. The magnitude R of an earthquake of intensity I is given by the following model. R equals log of I. Intensity is measured by wave energy. So have you ever seen like the movies and they're like looking at, or even sometimes you'll see it on the news, if they're looking at earthquakes, right? You see the seismograph, that's the little like needle that moves back and forth. That's measuring the wave energy that is going on underneath the ground. And so that's basically what this I is representing, is the intensity of those waves. So, just this year, there was a earthquake in the Philippines, and it had a Richter scale reading of 7.4. So if I wanted to go backwards, right, so this is what's given, is my Richter scale rating. We're wanting to go backwards and find what our intensity is. Yes? So again, what they give me, what I'm looking for. So my R is 7.4, and my I is what I'm looking for. So this time, what type of equation do we have?
Logarithmic.
It's a logarithmic. So how do I get rid of logarithmic equations? So instead of taking the log, right, if I already have a log, what do we want to put it to instead? Yeah, we put it to the exponent. Now remember, we put it to the exponent of a base of whatever our base of our log is. My log doesn't have a base. What's my understood base there? 10. So this is going to become 10 to the 7.4. And again, 10 to that stuff is going to undo each other. So I am just going to be left with I. Yes? So then, if you plug that into a handy-dandy calculator, what do we get? A really big number, okay.
8,864.
What do we get?
2,511,8,864.
Yeah, so 1, 2, 3. So we have 25,118,864. Yes? Yeah. Which is why, right, like that's the whole reason why we have this Richter scale rating. Because like, would it be very much fun to refer to our earthquakes as like, that was a 25,118,000 earthquake? Not really. We like it when we can scale things down, like our mind. Like we understand that, oh, 7.4 is much bigger than a 5.0, right? It's much easier for us to just talk about it in that way. All right, so then next up we want to go the opposite way. So it says find the Richter scale rating for the November 17th OKC earthquake, which with intensity 251.1886. So I'm given opposite information this time. This time I'm given intensity and I want to find Richter scale. So I have R equals, again, log of I, which they give me I. So I actually don't have to do much solving this time. I really just have to plug that into my calculator. And what do we get? 2.3999. Okay, we'll go ahead and round to a 2.4. So it would have been a 2.4 on the Richter scale rating. Which makes sense, right? Because OKC, we're not super known for our like super intense earthquakes, but still relatively up there. What questions do we have there? Alright, that's all we've got.